close this, we won't need it. Okay, oops. A1, sketch a graph whereby you put force here and extension here. So, I don't have anything to show you, but this is the one, you know, where you stretch something, and what should the relationship between the force and the extension be? Proportional. Proportional. What's the name of this relationship? Come on, you keep forgetting his name. Hooke's law. So when there's no extension, no force. So the graph looks like this because you have F equals K delta X. Yeah? But then do you remember what happens if you stretch something too much? Now let's say it doesn't break, okay? Yeah, you reach what's called the elastic limit. So then what happens to the material?
It doesn't go back.
It doesn't jump back. It's like more plasticky, you know. So what happens is you stretch it until you reach one point here, which is called the elastic limit. And then what happens is it kind of goes flatter here. This region here is called the plastic region. That's when it gets all, you know, you stretch it and it doesn't really stretch back. And then, what else do we need to show? Oh no, that's it. So he wants us to show a graph, which is part 1, and then where's the elastic limit? There it is there. And where's the region of plastic deformation? That's it there. That's part 3. Yes, it kind of curves off. It's straight and then it curves away. That's 5 marks. That's good, okay. Well, I mean, draw it nicer to get 5 marks. Okay, a brass wire is 1.5 meters long. So you have a piece of wire here, and it's 1.5 meters long. Its diameter is 0.8 millimeters, and there's a weight down here of 5 kilograms, and Young's modulus is 1 times 10 to the 11. Determine the stress on the wire. So do you remember the formula for Young's modulus? What was the letter for Young's modulus? E, wasn't it? Yeah. So Young's modulus, what is the formula?
Stress over strain.
Stress over strain. Or is it strain over stress? Stress over strain. Stress over strain. You're freaking me out, guys. Stress over strain, isn't it? It's not strain over stress. Alright, before I look, let's take bets. Who's thinking stress over strain? Come on, hurry up. Okay. We're saying stress over strain? Be embarrassing if it was strain over stress. Come on. Oh, that's the problem. I'm connected to the accommodation building. Maybe I can, here we go.
Stress over strain. Yeah. Ratio of stress over
Stress over strain. Aren't we so smart? Okay. Now, do you remember what each one is?
stresses length over extension.
The other way around.
No, the
Extension over length. And what's the strain?
Load over effort.
No. It's force over,
Plus area.
very good, force over area. Now, do I have these the right way around?
No, that's one.
Isn't, I think it's the other way around, isn't it?
Yeah. Stress is
Stress is the
opposite.
force over area and strain is the extension over the length. Okay, now what is he asking us for? The stress. So actually, I don't need to get, I'll just call this stress. He wants the stress. Okay, that's not too bad. So he says here this is 10 to the 11. So if I just bring that up, it's 1.5. How long is it extended by? Actually, maybe I don't know it. Okay, maybe I have to put it in. F over A. What do I know in this formula? The problem is, I know the F, I know the A, I know the L. Yeah, I don't know delta X, so I should find that first. So what's the F? It's 5G. What's the A? It's pi r squared, which is 0.8 times 10 to the minus 3 squared, all over delta X, which I don't know, all over L, 1.5. Alright, someone give me a calculator and I'll do that. So, let's see. 5 times G divided by pi. Oh wait, 5 fraction. 5 times 9.8 over pi times r squared times 1.5 10 to the power of 11. And then dot. Okay, so I got delta X equals 3.66 times 10 to the minus 4 meters. That's my delta X. But that's not it. He wants the stress. Oh. I'm being stupid. I've just... A stress is just this piece here, isn't it? Yeah. Alright, sorry. So what did I just do? I just did this. I did part 2 there. That's part 2. Get the delta X. I actually did the more difficult part first. Okay. Next one is the stress, which is F over A, which is 5G over pi r squared. So 5 times 9.8 divided by pi, or what's the radius? It was 8.8, wasn't it?
Yeah.
squared. So that works out as 7757403. So I'll do 1, 2, 3. Yeah. 7.8 times 10 to the 6. Sorry about squishing that in on the bottom. I'm sorry, I did the more difficult part first and the easy part second. So the easy part was get the stress. That's just F over A. And then the more difficult part was to get that. Is that okay for you? Yes? Sorry? It's okay? You don't look okay. It's okay. Are you hungry too?
No. I have to go. No.
Speaking exam?
10 minutes later.
Ah, are you nervous?
Later.
Who's your partner?
I don't know him.
What's his name?
I don't know, it's a long name.
Anyone know who this could be?
No.
It is from
Lonely.
Saudi.
No.
So PhD.
It's long.
Alyssa?
No, I'm still looking at
Spell the name? A-E-R? A-D?
Something. I don't
Think
remember.
Abdullah?
I'm remember.
Abdullah.
The last letter is A.
Yeah.
There's I don't know.
One of my cousins.
Oh, yeah, maybe one of the Abdullahs. There's two Abdullahs, yeah.
Yeah.
One of your cousins, maybe, yeah. Which would be the better speaking partner?
Both.
Both?
Yeah.
You should be very nervous.
I hate speaking.
Why do you hate speaking? You do such a good job, right?
Yeah.
Don't we all think so?
That's good.
Yeah.
What's this?
Huh? Okay, next one now. Boyle's Law. So who remembers what Boyle's Law is?
pressure.
Pressure.
Pressure
Inversely
proportional to
volume.
volume at
Constant temperature.
constant temperature. Okay. Now, next one here. Volume equals 2 times 10 to the minus 3 meter cubed. N equals 1.5 moles. Temperature equals 300. And they want the pressure. So what's your formula here? PV equals N or T. So P equals N, which is 1.5, or which is 8.31, isn't it? T, which is 300, over V, which is 2 times 10 to the minus 3.
1.87
Pascals.
10 to
What?
past 6.
Times what?
10 to past 6.
Okay. Yeah? So it's 1.87 megapascals. Okay. Part 2. How many helium atoms are in the cylinder? Now, we have to use the fact that we know how many moles there are. How many moles are there?
4.
1.5 moles. Now, what is the No, we'll get to Avogadro in a moment. What is the molar weight of helium?
4.
It's 4, isn't it?
4.
Yeah, 4, 4. So, the way it works is, what's Avogadro's constant? You use the letter L, isn't it?
6.27.
6.02 times.
10 to past meter.
Okay, so we want to know, okay, no, this is easier than I thought. He wants to know how many atoms of helium there are. So So it should just be a matter of multiplying this, right? Well, how many marks is this?
2.
2. Oh yeah, okay. So if you multiply these together,
9.
what is it?
9.02.
9.03.
Times 10 to the 3rd.
Alright. If the molar mass of helium is that, determine the mass of one atom of helium. So that means 1 mole of helium is that much, yeah?
What if we know already one of us?
Can you just give the answer? Don't know if they'd like that. 1 mole equals, what is it? 4 times 10 to the minus 3 kilograms. Oh, this is too easy. So then 1 atom would equal this divided by Avogadro, which is 6.02 times 10 to the 23.
6.64
Yep.
times 10 to the power minus 27.
That seems right. There's one way you can check if this is right, okay? How many protons and neutrons are in helium?
2 and 2.
2 and 2, so in total 4. So this answer should be roughly for U. And remember, U is the mass of 1 proton or 1 neutron. So look at the table book, and what is U? You can see that U is 1.66 times 10 to the minus 27. So yeah, it is roughly a quarter of it, isn't it?
Yeah.
Now it won't be exact, it's only rough.
Yeah, it's the exact value.
What's that?
It's the same.
Okay. Right, okay, now next one. Part 3, part 1. A quantity of gas is now released from the cylinder until its pressure has fallen. The temperature remains constant. Determine the number of moles of gas remaining in the cylinder. So what's happened now is they've let some of the gas out until the pressure has fallen. Yes? Is that okay? So you could use PV equals nRT. Now what does he say is constant? What's constant here? The temperature, yeah? Look, come on, focus, people, focus. What's constant?
Temperature.
And what else would be constant?
R.
R. What's changing?
Number of V.
And, yeah, and what else?
V.
P.
B.
But I don't think V is changing because it's in a cylinder, isn't it? So it's like if this was full of gas and then I just opened it and let the gas out. I think the V should be the same. What do you think? Would you think so too? So we'll say the V is the same. So if I rewrite this, I get P over N equals RT over V. So this is constant. Okay? So at the start, what's the pressure? He says it's, we calculated that. That was our answer from earlier. It is 187 megapascals. 1.87, sorry. And then what's the N? Did we calculate? It's 1.5 moles. Now that's constant, right? So that should equal the P over the N at the end. Now what's the P at the end? It's 5 times 10 to the 5. And the N at the end, we'll call it N2, we don't know. So a little bit of rearranging. 1.5 times 5 times 10 to the 5 over 1.87 times 10 to the 6. What's that?
0.4.
What is it?
0.4.
0.4 moles left. Last one now. How much mass has been lost? So, how much is lost? 1.1 moles. But didn't he give us the mass of 1 mole earlier? He did, didn't he? It was, remember? Here it is here, 1 mole equals this. So all I need to do, multiply this by 4 times 10 to the minus 3, and I get
4.4. Minus 3.
oh, well actually what's 10 to the minus 3? That's just gram, isn't it? So you can say 4.4 grams lost. Yeah? I think number 6 actually it's a good question. Do you think it's better than the simple harmonic motion or the same? I think after doing this now, I think this was easier than simple harmonic motion. So actually maybe this year we should have done, or you should do this, Newton, and what's the other one? The radiation one. Okay.